my great pleasure to have today's colloquium Professor Martin Aero, Fields medalist. He got a Fields medal last year, in particular for his work on regularity properties of stochastic differential equations. He is now a leading expert in this field, and he has, among other things, also worked on the construction of lacuna from stochastic systems, general ergodicity theory, multi-scale analysis, and the technique of path sampling and theory of graph path integration, which we saw in these stochastic differential equations. Besides his Fields medal, he also got other prizes, and just to mention the Dalmar prize, the Warwick prize, the fellow of ANS. It's a nice pleasure to have him here. He's actually now at MSRI visiting, and he was so kind as to use the opportunity to respond kindly to my invitation and come here. So and now I think I have said enough, and I want to give the word to Martin.
Thank you. Thank you very much for the invitation. It's a pleasure to be here. Beautiful campus. So now, okay, so maybe sort of wondering what kind of infinities I'm going to talk about. So obviously, since I'm more of an analyst or probabilist, I'm going to talk about infinities of the analytic kind. There aren't going to be any big cardinals or anything like that. And actually more specifically, so the kind of infinities that I want to talk about, they first appeared in the context of the development of quantum field theory. So that goes back to the 20s. And in the late 20s, people started writing down a quantum theory of electrodynamics. Okay, so they wanted to unite quantum mechanics and electrodynamics, Maxwell's equations. And so, they do the usual thing that physicists do, which is you try to make an educated guess of what your theory should look like. So you write down a Lagrangian or Hamiltonian or something. And well, this usually depends on the number of parameters. Right? So you write down some kind of Lagrangian, and somewhere you would have the mass of the electron or the charge of the electron appearing in there. So you have a bunch of parameters in this Lagrangian. And then what you do is you use this to make predictions, and so prediction is make some kind of experiment, and your theory is supposed to predict a certain outcome for this experiment. And then what you do is you just make sufficiently many experiments so that you can determine the parameters in the theory, and then once you've determined all of them, you can make new predictions that you can then sort of verify proof of this proof of theory. Now, in this particular case, if you want, the theory is relatively complicated, and so it's difficult to use it to actually really predict the outcome of an experiment. You can predict the outcome as some kind of a power series. Okay, so you can get approximations if you want of the outcome, and the outcome would be a probability that something happens. And it actually comes naturally as a power series in a constant which is called the fine structure constant. It is worth roughly, almost exactly actually 1/137. And so the idea is that this is, 1/137 is some kind of epsilon, right? But epsilon is really worth, it has a physical meaning. It's actually 1/137. It's not arbitrarily small. But still you have a power series in epsilon that comes out of the theory. And so what people first did is they just computed the first term. Right? So okay, so we compute the first term. That allows to make certain predictions. So you have an approximate theory, which allows to make certain predictions, and it worked actually pretty well. And then I think Oppenheimer was one of the first to try to go to the second order. Okay, so let's do the second order approximation. And what he realized is that the problem then is that for many outcomes that you would want to compute, already the second term, sort of the coefficient, if you want, in front of alpha squared is infinity. So the problem is not that you have a power series in alpha and maybe the coefficients get too big, so you don't really know whether the radius of convergence is 1 over 137. The problem is way before that. The problem is that the second coefficient is infinity, and all the coefficients after that are infinity as well. So then, it's not clear what you're supposed to do. Right? And, well, so the first reaction, of course, would be to say, well, obviously the theory is rubbish, so you throw it away and you try to build a new one. But they had some confidence in the theory. And so they came up with the following procedure. So here's a number of people who came up with this, and particularly actually, I think Schwinger, Feynman, and Tomonaga shared the Nobel Prize for that. And, well, the idea is the following, is that the way these infinities show up in the theory is basically because these coefficients are obtained by computing some integral, and the integrand ends up having a non-integrable singularity. Okay, so you want to integrate some function, and the function diverges, and diverges too fast, so when you integrate, you get infinity. And so what they said is, well, let's just take that infinity as a new parameter in the theory. We just pretend it's finite. Okay, and we take it as a new parameter, and then we just have it gives us an extra parameter. We just have to determine it. And the idea was to try to do that in a kind of systematic way, in the sense that when you go and compute the different terms in the expansions, the kind of singularities that appear are always sort of the same. So if basically the idea is that if you have the same singularity appearing twice, well, it's supposed to be the same infinity. So if you pretend that that one's finite and you give it a value, you would have to give that one the same value, right? And then what they figured out is you can do that in a pretty much in a systematic way, so that you can get away with only finitely many new values. Now, of course, that sounds like a horrible. I mean, from a mathematician's perspective, that sounds really like a horrible cheat. And well, they actually didn't quite like it either. Right? So here is a quote by Dirac who says, "This is just not sensible mathematics. Sensible mathematics is act in a quantity way. It's small, not because it's infinitely big and you just don't want it," which is essentially exactly what they did, right? So here is Feynman. Said the shell game that we play is technically called renormalization, but no matter how clever the word, it's still what I would call a Dippic process. So, it clearly sounds like a cheat, but it works. Yeah, I mean, you can do that. You can make predictions. It actually works extremely well. And, by now, I mean, quantum electrodynamics can be verified to extremely high accuracy. There are certain predictions you can. That's one of the numbers that gets often quoted. How amazingly accurate quantum electrodynamics is. So let me try to explain to you in a slightly more systematic way how this cheat works and how you can interpret it in a way that doesn't quite sound like cheating. So the first thing is that from a physicist's perspective, it's actually perfectly legal. In the following way, that, after all, what's a physical theory? It's just something that takes an experiment and gives you a recipe for computing the outcome, computing a prediction for the outcome of the experiment. And now, nobody prescribes a priori what the recipe should be. So if you can come up with a consistent recipe to predict some outcome, good for you. I mean, there's nothing illegal about that. Even if maybe you write down some kind of formula and what you're actually doing doesn't quite correspond to the formula that you wrote down. Now, but there is a bit for more slightly more systematic way of understanding what's going on here. And so let me try to give you some kind of a cartoon. So here is again a sort of general physical theory. So a general physical theory has a bunch of parameters, right? So that would be things like mass of the electron, things like this. And then it's essentially a map that takes as an input these parameters, an experimental setup, whatever that means, depends on the context. And then it gives you as an output, say, a real number. Okay, I mean, it could be something else, but essentially whatever you get as an output, at the end of the day, you can boil it down to a bunch of real numbers, right? Now, what happened in this situation is that you had some kind of a recipe for computing your map n, but the recipe would give nonsensical answers. Right? It would just give you infinity as an outcome. So what you can do is you could try to somehow regularize it. Right? So for example, I told you that the reason why the outcome was infinity is because there was you were trying to integrate some function that wasn't integrable. Right? So there was some divergence involved. And so you could say, well, okay, so that divergence somehow corresponds to some behavior at very small scales. So you could argue that at very small scales, my theory is just not a good description of reality, so I replace it by something else. And so I just replace it by something that, caps off these divergences, right? And so now I have a theory which depends on the parameter epsilon, which would be, like the scale at which I cap things off. And it maybe also now depends on additional parameters, and they're sort of the unphysical parameter, if you want, which tell me how do I cap things off, right? So I have to make a choice of what, I have to come up with something at these small scales. So I come up with something, but I could have many different choices, right? And so I end up with a whole bunch of new parameters here. And the idea is that these are sort of unphysical because they describe, things that I don't care about and I don't really believe in as being a good description of reality anyway. It was just some kind of placeholder for getting something at very small scales to make things work, right? Now, of course, if you just do that and then send epsilon to 0, you're back to the problem you had in the first place, right? The things are just going to diverge. Now, however, in many cases, and we're going to see a number of situations like that in the talk, there is a group, I call R here, which acts on that space of parameters. Okay? And this group is not going to be common. So think of this as being something like Rn with addition as a group operation. Okay, so something like that. And now what you could do, the idea is that as you send epsilon to 0, you're going to use this group action to adjust the parameters in here. And you want to adjust these parameters in just the right way so that it creates cancellations so that you get convergence to a finite quantity. And it turns out that in some situations, you can even do it in such a way that now, whatever, if you want the value of these unphysical parameters here, which you don't really want to care about, right? So you choose any, if you want, procedure for capping things off. So that would be this eta here. And then whatever the eta is, you can find a sequence of these group elements that typically is going to diverge as epsilon goes to 0. So that if you compute that limit, you get a finite limit, and not only you get a finite limit, but you get a finite limit which doesn't anymore depend on these unphysical parameters. So in that sense, what you've done is you've replaced your theory by something more or less arbitrary at the small scales. But then you've taken a limit where the small scale goes to 0, and by tweaking, if you want just the physical parameters of the theory, you manage to get a finite limit, and the finite limit, which furthermore doesn't depend anymore on how you cap things off at the small scales. And now this is what people would call the renormalized theory. Okay, so this now is something that computes perfectly finite values. Whereas the naive thing, which is just don't do anything here and send epsilon to 0, is just going to make things blow up. And so at the end of the day, here you see the outcome is you get a theory which has the same number of parameters as the original theory, right? So it still depends on the same parameter space here as the theory you started from. And the moral of the story here is that sometimes, if you want, sort of the form of a model sort of matters, even though the kind of the finiteness of the constants that appear in it doesn't matter so much. Okay, because that's kind of what happens here, is that you're actually sending some of these constants appearing in your model to infinity in order to create cancellations that allow you to compute finite values again. And so here this guy, so Holt, for example, so he shows, well, he obtained a Nobel Prize for physics showing that the standard model, which is the best shot one has at describing reality if one neglects gravity, is in some sense renormalizable, more or less in the same sense as what I just described. And well, that model basically still stands. So as far as I'm not a high energy physicist, but as far as I know, for the moment, it's the best shot for class. Okay, so now let me give an actual example. Okay, so this was a bit wishy-washy. Let me give you an actual mathematical example. So I'm going to take a situation where, if you want, the world is described by just a distribution. Okay, and what is a distribution? It's something that, well, it's a linear map that takes a test function, gives you a number. So if you want, the test functions play the role of the experimental settings. Okay, and the theory takes the test function, gives you a prediction, which is just a number. And now, let's say that I have, for some reasons, I have reasons to believe that my reality is described by a distribution of that type. Okay, of the type sort of constant over x, of absolute value of x, minus some constant times delta. Now, obviously, this is actually a silly guess, right? Because the way you assign a distribution to a function is by just integrating it against test functions. And obviously, the function 1 of absolute value of x is not integrable, say, on R. Okay? And so I don't actually have a canonical way, if you want, of testing this against a test function. Now, because I know how to test it against test functions that vanish at the origin. Right? So if my test function phi vanishes at the origin, then it cancels out that singularity, and then there's absolutely no problem in multiplying by 1 of absolute value of x and integrating over R. So I have some sort of partial specification, if you want. And so what I would want to do is, well, in some sense, I would want to set that constant here to infinity, so that it kind of cancels out the infinity that comes from the singularity at the origin of that guy. Now, how do you do this? Well, here is how you can do it. Okay, so you can just, well, just give an explicit formula, but what do you do? So you just take a cutoff function, that's the chi here. So chi is just a function that kind of looks like this. Okay, so it's any function that looks like this, which is 1 here, and then 0 away from the origin. And then what you do is you just subtract from your test function phi this chi of x times phi of 0. In that case, in that way, you force it to vanish at the origin. Okay. Now there's no problem in dividing by absolute value of x. So you can do that. This converges perfectly nicely, and if you want, you can still subtract the multiple of phi of 0. And what you see here is that, well, first this gives you a perfectly nice distribution, right? It's linear in phi, it's defined for every nice test function. So that's a perfectly nice distribution. And you also see that you could have obtained it in the following way. You could replace, for example, the absolute value of x by absolute value of x plus epsilon. done. Right? So if you do this, then dividing something by absolute value of x plus epsilon is absolutely not a problem. It's perfectly integrable. It's just going to diverge if epsilon goes to 0. Right? But you see that here, if I replace absolute value of x by absolute value of x plus epsilon, then both of these parts in the integral make sense separately. Okay, as it stands here, they don't. And so each of them separately diverges. The difference is perfectly well defined. If I put an epsilon in here, then both of them make sense separately. The first one is exactly the thing I wanted to have here, well, an approximation of it with x plus epsilon. And the second term here is of the form something times phi of 0. So it's actually just a multiple of the Dirac distribution. Right? So actually I have a very natural approximation of this guy, which is obtained by just replacing x by x plus epsilon. But then, if I want to get finite limits, as I send epsilon to 0, what I have to do is that in this constant here, I have to subtract, well, this term here, which is going to blow up, and in this particular case, it's going to blow up like log epsilon. But you see, it's exactly of the type that we've seen before, in the sense that the unphysical parameters here are, whatever procedure I choose to regularize the thing at the origin. Instead of putting x plus epsilon, I could have put the square root of x squared plus epsilon squared, for example, or whatever I wanted. You would always get the same limit, actually. Right? So if you just regularize this and then subtract the suitable multiple of phi of 0, if you choose that multiple in such a way that you converge to some limit, the limit is actually always going to be of that type. So you're exactly in the situation of the previous slide. Okay. One thing that you see here is that so that's a sort of a point to think about, is that in doing this, you've somehow lost the choice of a canonical origin for this constancy here. Okay, in the following sense, here there was some freedom in choosing that test function chi. If I choose a different test function chi, well, I get something different, but it's really not that different because it only differs by a finite multiple of phi of 0, and so I could have obtained it just by changing the value of that constant. Right? So I really get the same limit, just a different value of this constant. But now there's no canonical choice here for that test function, right? So the most canonical choice would be to take that guy just equal to 1, right? To simply have here phi of x minus phi of 0. That would be the most canonical thing to do. But then you would have the problem that this integral doesn't converge at infinity. Right? So it's just that the problem of divergence at the origin would just be turned into a problem of divergence at infinity. So that doesn't work. So there's no canonical choice, if you want, of that chi, which is the same as saying that in this two-parameter family of distributions that you get, there's no canonical choice of origin for the second parameter. Okay, so the second parameter is a real value, but in some sense it's a real value without an origin. So of course, every fixed choice of test function gives you an origin, right? But since there was no canonical choice there, it tells you there's no canonical basis of the origin. And that actually appears quite often. Now, so here is an example which appears completely unrelated to the previous one. So here, now let's do some mathematical finance, some daily mathematical finance. So you probably all know what a random walk is. You just take a bunch of independent random variables, all with the same distribution, and you kind of add them up. And each guy is supposed to be just the value of a step. And now if you take a random walk and you run it faster and faster, so instead of making a step every unit of time, you make a step every epsilon unit of time. And you rescale space in such a way that the size of the steps is not all the 1, but all the square root of epsilon. That's the correct way of rescaling. Then, as you send epsilon to 0, your discrete random walk converges to a random continuous function, which is Brownian motion. Okay, and that actually doesn't really depend on what kind of steps you take, as long as the steps have mean 0 and you don't make sort of too big steps. And so this is what the Brownian motion looks like. Okay, so in the limit you get some kind of random continuous curve. The idea being that, well, epsilon here has been set to 0, so the individual steps are sort of infinitely small, and so you don't see any discrete steps anymore. You have a continuous curve, but it's still extremely rough. And as a matter of fact, you can show that it's Hölder for every Hölder exponent less than a half, and it's actually not Hölder half at any point. Okay, so it's basically almost Hölder half. That's that kind of regularity. Now, let's take a simple model for asset price. Now, asset price, something like a stock price. So you can think of epsilon now being sort of the time between ticks in the stock market, and at every tick, the price either goes up or down. But now the amount by which it goes up and down is not quite sort of always identically distributed. Typically, it's actually proportional to the price of the stock. Right? So if you have a stock that's worth $100, then maybe in a tick it could go up by $1. Whereas if the stock is itself worth only $1, well, obviously in a tick it's going to move maybe by a cent, so not by much more. Right? So it's much more natural to have a model of that type for the stock price, right? Which is basically the same type of model, but where now the amount by which the price changes is proportional to the price itself at every step. Now, if you just look at this expression, you can rewrite it if I write delta S for simply the difference between the price at the next tick and the price at the current tick, and the same for the random walk. You can rewrite this as in the delta S is S times delta W. Okay, delta S being difference between these two is equal to S times that, and that guy is the difference between these two. Okay, so I've just rewritten that identity. And now if you sort of squint at this, this looks like, if I divide by delta t, well, these deltas kind of look like these, and it looks a bit like an approximation to a derivative, right? So in first year calculus students would have absolutely no second thoughts in saying that, you send epsilon to 0, and therefore, well, this is going to be converged to the solution to the differential equation, ds by dt is equal to s times dw by dt. And that differential equation, I can solve it. The solution is s0 times exponential of w. Except that that's wrong. Okay? So it turns out that if you do this and you pass to the limit, then actually what you get is not s0 times exponential w, it's s0 times exponential w minus t over 2. And you could actually have guessed that, well, at least you can certainly guess that this is the wrong answer, because if you take expectations on both sides here, just by independence, that guy is supposed to have expectation 0, so on average the thing just move. So by independence, the expectation of that guy is equal to the expectation of that one, so it doesn't change. So even if you go to the limit, it still doesn't change. Okay, so the expectation should not change over time, whereas the expectation of the exponential of a Brownian motion, one can just compute it, and it turns out to be e to the t over 2. Okay, so well, that expectation changes over time, so it cannot be the right answer. Whereas here, the e to the t over 2 just gets cancelled out by the minus t over 2 here, and so indeed the expectation remains constant. Okay, so this is at least a more plausible candidate for the limit than this. But now, what actually went wrong, right? Because we almost had a proof that the limit should be this. So where did the proof go wrong? Well, the problem is that in our proof, well, we had an s times an increment of the Brownian motion, divided by the corresponding increment of time, and then we said, well, the limit, this is something like an s times dw by dt. And of course, you know, you remember what the Brownian motion looked like. It was something very rough, and certainly not differentiable anywhere. And so it's not clear, so you have some sort of weak derivative, that's fine. But then you multiply it by, you know, the solution of this equation, which itself is going to roughly look like the Brownian motion. And so you have a distribution which you multiply by a quite irregular function, and it's not clear whether you're allowed to do that, right? You can multiply a distribution by a smooth function, but not by a continuous function in general. And actually there's a theorem which says that if you have, you know, a function and a distribution, the product is well posed. Basically, if your function is Hölder alpha, and your distribution is, well, Hölder beta, but for negative beta. And what that means, well, Hölder minus a third basically means that you have a derivative of the function which is Hölder plus 2/3. And so you can give a definition of somehow negative Hölder regularity. It works in higher dimension also. Then this product is actually well posed if and only if the sum of these exponents is positive. And in our case, well, the regularity of Brownian motion, remember I told you it's just below a half. And so the regularity of its derivative is just below minus a half. And since the solution is expected to look like the exponential of a Brownian motion, it's also going to have regularity just below a half. And so you're in the case where that's just below a half, that's just below minus a half, and so the sum is just below 0. And well, this is well posed if and only if the sum is above 0. So you're just on the wrong side of that borderline. Okay? And so as a consequence of being on the wrong side of that borderline, if you take different approximations of that very simple ODE, just the ds by dt equal s dw by dt, if you take different approximations, they converge to different limits. Okay? So for example, if you took a kind of symmetric approximation like this, then for this you can actually prove that it converges to the limit you would expect. But you can cook up, you know, any number of plausible looking approximations for that ODE. And it turns out that it will actually always converge sort of pretty much any plausible looking approximation to that ODE will converge to a limit. The limit will always be of that type. And it's just that that constant is going to change. Right? So that constant was a half in the previous example, and it would be 0 in this example. If you know, by looking at different approximations, you can make it basically any value that you want, actually. So the moral of the story here is that when you have these quite singular objects to deal with, sometimes, and that was kind of the moral of the story in the very first slide as well, right? So the limits might depend on the details of the approximation, but actually not really, in the sense that it just gives you a parameter in the theory, or maybe 2, maybe 3, but it gives you just a finite number of parameters in the theory. And at the end of the day, you still get, you know, the possible limits that you can get depend just on very few parameters, much fewer than somehow the possible approximations that you could write down. Right? So here there are lots of different ways of writing some sort of difference equation that looks like a plausible approximation to that ODE, but the limits that you get, they're all just parameterized by one constant. Okay. So now, again, apparent change of subject, but we'll see it's going to be again related to the previous examples. So I want to say a few words about this notion of universality in physics. So universality in theoretical physics is this idea that if you have a system, especially random system, which is such that that at large scale, so it has microscopic randomness. Okay, and microscopic randomness typically means lots of different random inputs, with each of them having essentially a negligible effect on the outcome. but they sort of pile up in such a way that, macroscopically at large scales, you still see something random. And the idea is that whenever you're in that type of situation, what you see, the kind of random thing you see at large scales, doesn't actually depend on the details of the microscopic system. So it doesn't depend on the details of what happens at small scales. Just like the Brownian motion, right? So you get Brownian motion, whatever the details of the random walk that you take a limit from. Right? So it's like the central limit here. You always get a Gaussian. You can add up any kind of IID random variables as long as they have finite second moments. If you divide by root n, you always get a Gaussian in the limit, whatever you start from. Okay? So here is an example which is much, much less well understood than the Gaussian case, and that's the case of interface propagation. Okay, so interface propagation, so here the example is you take a sheet of paper and then you put an electric wire at the bottom, you zap a current through the wire that ignites the sheet of paper, and then you track the flame front. And you just take a picture every second or every few seconds, and these are the successive snapshots of the flame front. And you see it starts off relatively flat, and then it gets more and more wiggly. So here you have this bump, and the bump actually gets larger and kind of spreads out, and you have new bumps forming. And what you're interested in is having some kind of description, of the space-time behavior of these random fluctuations. And here is another example, which is, so these two are actual data from actual experiments, actual physics papers. So that one is a layer of liquid crystal that comes in two phases. One of them is unstable, the other one is stable. You prepare it in the unstable one, you zap a laser beam at it, the laser beam gives you enough activation energy to turn it into the stable phase, and then you have that thin line in the stable phase, and that one expands, sort of invades the unstable one. And then again, you take a snapshot every second also, and the different colors here. Here, color is time. Okay, so you have this front here, and again, it kind of moves up, and the fluctuations get larger and larger. And they roughly look the same. Okay, I mean, you can make mathematical toy models. So here are three completely different types of simple mathematical models, which have the same kind of features. So it's something that grows in some random way. So let me show you what's the kind of models that I have in mind. So this one, so that's the Tetris model. Okay, so you just take, imagine a Tetris game, sort of infinitely big Tetris game, where you simply don't have a Tetris game player, you only have a Tetris game, and the bricks just pile up according to the rules of the Tetris game. And, well, you have an interface that separates the bricks at the bottom and the no bricks at the top. And, well, here the interface looks, well, you don't even really see much of an interface, but if you zoom out, right, you kind of zoom out and you let the thing go faster and faster. And you see something like this. Okay, so now you have hundreds of thousands of Tetris bricks here. They fall down really fast. And you have this interface here that separates the Tetris bricks from the no Tetris bricks. And you see that this interface here, again, looks pretty much like these type of interfaces that you have here, or the kind of interface that you have here from the liquid crystal experiment. Now, mathematically, fortunately, this is still very poorly understood. So there's essentially one type of models, and so in this particular case would be the third one. There's one type of models where you have some kind of integrable structures which allow you to get explicit formulas for certain observables. So Harold Whittle is an expert on this, so he famously obtained one of these, together with Kirk Facey, they obtained famously one of these explicit formulas for actually exactly that model, which then allows you to take asymptotics and compute, for example, the fluctuations here above 1 point. And what you can prove in this model is that as time goes to infinity, if you look at the fluctuations above 1 point, they converge not to a Gaussian distribution, but they converge to a random matrix distribution. And that has now been, so there have been lots of works in this direction recently, also by Sasamoto-Schbohm and Borodin, Pascal, Holwin, etc. There are several groups of people who work on these problems, and they showed that now there's a whole class of models that they've identified that has similar features, and for all of these, you get the same limiting distribution, and actually they can compute. So for example, for certain models, you can prove that you can get a description of this whole process at fixed time. So there's no description yet of the full space-time process, if you want, even in this large scale.
Are these surface fractals?
Right, so this guy, we're going to see, but so this guy has the same kind of scaling behavior as Brownian motion. Locally, it looks like a Brownian motion. And so it is polar half, but not better at any point. So in particular, if you take, for example, the curve as a subset of the plane, it would have fractal dimension 3 halves. Yes?
Is there any connections between, at least I'm thinking about the Tetris process, between what you're seeing played out and uniform random variables, in this sense that the way you generate this process.
Right, so for example, in the Tetris case, while you generate, the next brick is just, the location of the bricks are just uniform.
Mm-hmm.
That's all. So the next
Can you,
brick is just
but
uniform.
sort of what I'm wondering is the location of the brick is uniform and which type you choose is also uniform.
But
Can
that
you,
doesn't matter.
can you derive anything based on that? Because it seems like it sort of gives a complete description of the system, at least on the small scale.
Oh, it gives a complete description, but it's just horribly difficult to extract anything from that description.
Mm.
Now, of course, I basically gave you the description, right? That was the point of the simulation, is that since you all know the Tetris game, that essentially gives you a complete description of that instantly, because you know what the Tetris game is supposed to do, and it just does that. Right? So you have a full mathematical description. It's a well-defined model. You have a full description of the model, but then you have to extract something from it. And in this particular case, in the case of this Tetris model, there's actually a simpler model, which is called ballistic deposition, and that one has been studied much more. Mathematically, there's almost nothing which is known. Okay, so the ones for which something is known are those models where you have additional special structure that allows you to compute certain quantities. And so what I'm interested in is, trying to be able to say something for, those models where you don't have this special structure that allows you to compute things explicitly. And so since it seems essentially hopeless at the moment to just take one of these models and try to show that the scaling limit converges to something. On the other hand, there's a class of models that's somewhat much better understood, which is the ones where these fluctuations are symmetric. So in this, like in the Tetris model, they're completely asymmetric. Right? So the Tetris model grows, and it never goes back. Right? It only goes up, it never goes down. I don't have lines that get killed. Now, you could imagine also some models where things can go up, and they're also allowed to go down. And they're allowed to go down with exactly the same mechanism as the mechanism that makes them go up. So you could make a model of fluctuations which is completely symmetric between up and down. And those models, one has a complete description of what the large-scale behavior is supposed to do. So there, the large-scale behavior is supposed to be Gaussian, and one has a complete description of all the correlation functions. So if you know that it's Gaussian, then everything is just described by the covariances, and one has covariances. So there, everything is, in some sense, everything is known, even though it might still be a very difficult problem for any one particular model of that type to really prove that it converges to that Gaussian limit, but at least you have a clear conjecture of what the limit should be. And So now the idea is so you want to look at something sort of crossover regime, which is take a model which is symmetric. So there you know that at large scales you're supposed to see these Gaussian fluctuations. And now make it slightly asymmetric. Okay, so make it slightly more likely to go up rather than down. Then what you expect? So you expect that, if you just zoom out a little bit, you shouldn't really see the difference between this and the symmetric one, because you only have a very weak asymmetry. And so if you zoom out, not too much, then you should basically just converge to, again, this Gaussian limit. On the other hand, if you start to zoom out more and more, at some point, you should see the effect of this asymmetry. So eventually, if you just take the complete scaling limit, you're supposed to get the same scaling limit as for the Tetris model. Okay, so you're supposed to see these random matrix distributions, which for an arbitrary model, basically nobody has a clue to prove that. And well, so the idea is to say, well, there's going to be a point somewhere where it tries to cross over between the two. Right? So it's going to look Gaussian up to a point, and then it's going to start looking like random matrix distributions. And well, there's going to be some point where it crosses over from one to the other one. So what is it going to look like there? And so the conjecture is that basically any model of that type at this crossover point is going to be described by the solution to this stochastic partial differential equation. Okay, so here you have a stochastic partial differential equation. So h is just the fluctuation of this height, which is a function of space, the x variable, and time, the t variable. And it follows something like a heat equation. There's a nonlinearity here, it's the square of the derivative. Then there is a noise term, and you should think of this as being something like independent random variables at every point in space and time. Okay, and there is a way of making this precise mathematically, but that's kind of good enough. The idea is that since you've zoomed out, so the randomness that comes, for example, from which brick you've chosen or where exactly the brick falls down, well, by the time you've zoomed out, things are just independent at every single point in space-time. Right? Because sort of the distance between neighboring slots becomes infinitesimally small. Right? So you should have some term like this. And, well, so you would like to prove a result of that type. So you take one of these weakly asymmetric models, you zoom out to just the right range where you have this crossover happening, and there you should see behavior given by this stochastic PD. Now there's an obvious problem in the very beginning, which is that, well, here is a simulation of this stochastic. Okay, so this is a just real-time numerical simulation of the solutions of this stochastic PD. Now, if I freeze time, this should remind you something. Right? I mean, it looks very much like this Brownian motion that we've seen previously. Right? And actually, that's a theorem. So you can prove that locally solutions to this stochastic PD look like Brownian motion. But now there's an obvious problem, right? I told you that Brownian motion is actually nowhere parallel half. And now you're supposed to take the derivative and square it. So obviously that's nonsense, because it doesn't have a derivative anywhere, so it has derivatives in some weak sense, but then you're supposed to square that, which you clearly know how to do. And so it's not clear probably what you actually mean by the solution to this equation. Now, again, we can...
You suppose it was hold slightly bigger than half.
That
How
would
big
still
would
not
it have to
help.
be?
Well, it would have to go to 1, right?
H1.
It would have
To be L2.
right. You would have to have a weak derivative. The weak derivative should at least be a function, and ideally an L2 function, because you would want the square to be integral, so you can at least test against test functions. And it's way below that. So you're missing a whole half derivative here. So it's not like the previous examples where you were just below the borderline, right? So here you have a derivative below the borderline. So now what you can, so here is something you can prove, which gives you some kind of well-posedness, right? So you do the same as before. You first regularize things. So here the problem, the reason why things look very rough is because of this noise term, which I told you is something like independent random variables at every point in space-time. So it's something extremely irregular. So you replace it by something regular. Okay? So you introduce an arbitrary scale, epsilon, and you just say, I replace it by something which has the property that if you take 2 points that are more than epsilon apart, it's independent. But then if they are less than epsilon apart, it's just something nice and smooth. Okay? So you just replace it by something like that. Say Gaussian, it doesn't have to be Gaussian actually. And then what you do is you allow this constant here to depend on epsilon. And the idea is that you want that constant to blow up in just the right way so that it cancels out the diverging part of the square of the derivative of that guy. Right? So of course, this guy at fixed epsilon is going to be nice and smooth. So of course the derivatives are going to be bigger and bigger, so if you square it, it's going to become enormous. And the hope is that as epsilon goes to 0, when you square it, if you recenter it somehow in the right way, you actually do get some kind of limiting distribution. And well, you can prove that. And furthermore, so the point here in the theorem is not just that okay, this converges to, you can choose the constants in such a way that this converges to a limit. The main point here is the fact that the limit is actually always the same. So the limit doesn't depend on the details of how you choose that guy. Right? So it doesn't depend on the details of how you regularize this. Okay? You always get the same limit, even though the constant that you have to subtract here depends on it very strongly. Okay, so this constant is going to blow up like 1 over epsilon, so even the prefactor depends on the details of how you regularize this. Yeah.
Was this independence a big surprise?
No, that's exactly what you would expect somehow, right? Because that's what physicists tell you, because you have universality. You always have universality.
I mean, that you can actually do
So-
it mathematically.
I suppose to some extent, yeah, so this, yes, people were somehow surprised that you were able to do it. In this particular case, if you take certain, if you only regularize in space and not in time, there's a trick you can play, and you could exhibit a certain limit before. So there was a notional solution, which of co-solution, which that goes back to Bertini and Giacomin in the late 90s, which is for this particular equation, there's a trick that allows you to exhibit something which is a plausible candidate for a solution. But it relied very much on time independence, so being white in time. And so that works as limits while you regularize in space and you keep it white in time. And then there's a trick you can play. And here the theorem is that you can also regularize in time. You can regularize in pretty much any way you want, and you always get the same limit. And that just it wasn't clear for a very long time, how you would even start proving something.
What's V equals 1?
Sorry?
V equals 1.
Oh, the space dimension. So it's the situation of the groove, space is really just one dimension. Okay. So here is another thing you can prove. So here, now in this result, we started from the object that we wanted to give meaning to, and we just did sort of the obvious way of making it regular, and then trying to get past to the limit. Now here is something which is, this type of universality result, which says I start from a model which is symmetric. So here is the heat equation with some, so here we have to assume that this is a Gaussian random field. You have some nice smooth Gaussian random field. If you take that guy and you rescale, this guy is completely symmetric under h goes to minus h. If you take the solution to this and you scale out, then this guy just converges to this white noise, and you have a kind of And now you take an arbitrary polynomial here. You take an arbitrary even polynomial, and you add, you sort of break this h goes to minus h symmetry by adding a term which is weak. Right? So this, remember, we want to be in this situation where you start from a symmetric model and then you add a weak asymmetry. Okay, so this is the weak asymmetry. So we put a small parameter in front to make it weak. And we take here an arbitrary polynomial. So think of, for example, just p of dxh as dxh to the power 4. Okay, so you don't put a square in, you put a power 4 instead. Or it could be a power 6 or power 10 or linear combination of that. And then the theorem is that, again, if you send epsilon to 0 and you rescale things, so here the correct choice of scale is 1 over epsilon in space, 1 over epsilon square in time, and then you have to dampen things, so it converges to a limit. Then it converges, not only does it converge to a limit, it converges again to the same object. So even if you start from an equation which doesn't have any dxh square at all on the right-hand side, it just has a dxh4, okay, you rescale this, there's a limit as epsilon goes to 0, and the limit is the equation I wrote in the previous slide, which just has a dxh square on the right-hand side. And the constant, if you want, in front of the dxh square depends on all the coefficients of that polynomial. So it's not just somehow that it picks out the coefficient in front of the quadratic term. It takes a linear combination of all the coefficients in the polynomial. And this you can describe it explicitly. You can understand why it comes out. Okay, so in the last 2 minutes, let me try to give you a somehow very quick idea of how you prove these kind of things. So I only want to focus on the first result, which is the one where you pick this KPZ equation, you regularize the noise, and you try to control it to show that there's a limit to regularization. It goes to 0. And of course, the main problem is to control this dxh square term, which is going to blow up. And so the problem, as we've seen, the problem is that the solutions in the limit aren't smooth at all. So what do we mean when we say that solutions aren't smooth? Okay, so, well, what do we mean when we say that something is smooth? If something is smooth, if locally we can approximate it by a polynomial. That's why it means to be smooth. Here, obviously, they are not. And so the idea is to say, well, actually, I'm going to make some kind of educated guess. I'm going to build a bunch of processes so that I make an educated guess that my solution locally is going to be well described by, again, some linear combination of those processes. But these processes are not going to be polynomials. They're going to be some random functions, space-time random functions. And now suppose I can do that, right? So suppose that locally around every point, I can describe my solution as a linear combination of a bunch of processes that I pre-compute, that I have an explicit description of, with coefficients that are themselves, the coefficients would be part of the solution of some fixed point problem. You have to solve PD to get the coefficients. But the objects themselves would be known in advance. Now suppose that you can describe your solution locally by such a superposition. Then of course the derivative of the solution is given by the same coefficients locally, just times the derivatives of these objects in some weak sense. And so now the square of the derivative, well, formally, locally, it would be described by the corresponding products of the derivatives of these objects. And so now the idea is to say, well, if I have these objects explicitly, then maybe I can just fudge around to show that the products of their derivatives converge to a limit. Now actually they don't, because, well, I know that for the solution itself, the square of its derivative doesn't converge to a limit, right? You have to subtract the large constant to make it converge to a limit. But then it turns out that, well, for these objects, you can do the same thing. So you can show, oh, actually, if I multiply them together, then, well, for some of them, the product actually does converge to a limit. For some of them, it doesn't, but you can make it converge by just subtracting a suitable large constant, or something like this. Or maybe you can make it converge by subtracting a suitable large multiple of another one of these objects, or something like this. So you can somehow fiddle around with these objects to make their products converge to a limit, modulo, fudging around. And then you can say, well, now I have some kind of candidate for a local description of the square of the derivative of my solution. Now the question is, if I have some sort of I have a candidate local description around every point, does this really describe a unique distribution, right? So is there a unique distribution on space-time which does coincide up to a certain prescribed order with this local description around every point? And then you can ask yourself, what are the conditions, the analytic conditions that guarantee that you have existence and uniqueness of such a guy? And that's how you end up controlling it. So you end up exactly doing this, right? So you end up, at the end of the day, you end up building your solution as a fixed point problem in a space of things that are locally described by linear combinations of certain objects that you pre-compute, that are sort of given in advance, for which you don't need to solve an equation. And in order to set up the fixed point problem, well, you have to, for example, show that at every point in the iteration, this analytical problem can be solved, in the sense that your candidate square of the derivative, sort of your candidate behavior at every point can be patched together so that it really describes one distribution. And you can do that. So you can do this in a way which is, at the end of the day, you can do it in a way which is uniform in epsilon, and in a way where you can control the limit, in the sense that the limit at the end of the day really depends only on these finitely many objects that you use in order to describe the solution. And for those, you can show that you obtain the same limit irrespective of the approximation. Okay, and that's essentially how you end up showing that the limit doesn't depend on the choice of approximation. So just some rough ideas. So I think I've already over time, so I stop here, and thank you very much.
Thank you very much for this very great talk. You actually could have continued still a little bit, but maybe we can have a couple of questions.
Just one last question on that. You referred to a fixed point. What fixed point methodology do you apply? I mean, the many fixed point theories out there.
So at the end of the day, it's just the usual Banach fixed point. At the end of the day, you turn everything into just a Banach fixed point. Yeah.
What does the KPZ stand?
Oh, that's Caldar, Parisi, and Jan. So they first studied it in the 80s.
With the same motivation?
Yes.
And if you look at this equation, what am I supposed to think of the solution a priori? Do you know where the H lies? Is that like one of the big parts of the problem?
That a posteriori comes out of the proof automatically, because you look for solutions that are locally described by da-da-da, and so it's going to have exactly the regularity of the least regular of these objects.
But that's after the proof, right?
That's after the proof.
And how do you try to, I mean, if you change the equation somewhat, is there a way to even like make a guess or make a sense of where that H lives?
So the thing is that, in some sense, in these type of equations, you have a lot of rigidity. So you see, in a way, you can't really change the equation, because you see, even if you You see, even if you tried here to put a power 4 instead of a square, as you rescale, the power 4 becomes a square. Right? So somehow this equation after rescaling, it looks like this. Right? So you have a bta or dx squared epsilon the same way as here. And the nonlinearity becomes actually an epsilon dxh4. Okay? So you take this, and the theorem is if you send it over 0 here, well, you get the same limit as if you replace that guy by just dxh squared. And so in particular, it also tells you that you're not allowed to put a finite constant in front of dxh4, right? Because already if you put a vanishingly small constant, you already converge to something which gives you a finite distribution. So in that sense, there's a lot of rigidity here. You cannot just change it by something other. Yes.
In the 1980s, a lot of physicists were playing with something called diffusion aggregation. I don't know if you're familiar. I was wondering if you're familiar with it and have some relevance to the things that you were talking about, because also there were just surfaces that were evolving and people were looking for fractal dimensions and so forth.
So I think that's still even less well understood. Yes, so there is something which is called diffusion limited aggregation, which would be essentially a model where you start from a seed, and then you have new points that kind of come from infinity and attach to it, but they attach according to a harmonic measure in the sense that if things they start filling up, then it becomes less and less likely that things attach here, attach to the boundary, and then there's the question of what does the scaling limit of that guy look like. So I think this is the it has somewhat a similar flavor. So there's recent work by Sheffield and Miller, and so what they looked at, so they conjecturally have some kind of 2-parameter family of random growth models that are conformal invariant in 2 dimensions. And so for one of the choice of these 2 parameters, that model would be the candidate for the scaling limit of this guy. Now the problem is that they can only build, so conjecturally the 2-parameter family, that they can really make sense of the model only for a curve in this parameter space. And the parameters for which it's supposed to be the scaling limit of that doesn't lie on the curve.
Are there further questions?